Next, we turn our attention to Q-value iteration. This is exactly the same algorithm as the original state value iteration, but now instead of the V's, the values of the states, we will use the state action values or the Q values. We begin with Bellman's equations again. For any arbitrary policy, pi, the Bellman's equations for the Q values are given by Q pi SA equals reward RSA plus discount times expected value of the future Q pi S pi. And the optimal policy, pi star, for that the Bellman's equation is here. All we have done is replace this Q with the maximum of the Q's, because when we are carrying out the optimal policy, then at every state S prime or S, we are always going to find the action which gives us the maximum Q. So these are the Bellman's equations. And as before, if we repeatedly apply the same equations over and over again, then that will give us the Q value iteration, and that will converge to the Q values, the policy-based Q values or the optimal Q values. And we shall actually prove this time, we shall look at a little proof that it converges to Q stars. Okay, so this is the Q value iteration for policy evaluation, and all we have done is for each state, and now for each action we have to carry it out. So we have another loop here for each action, for each state and for each action. This is what we have to do. And this is nothing but Bellman's equation. So now remember, we have a outer for loop. That doesn't mean that the algorithm complexity increased, because we had to do an argmax over all actions in our original value iteration. So the state value iteration and the state action value iterations actually have the same complexity, computational complexity. The only difference is you need some additional storage when we are doing the state action value iteration. For policy improvement, this is the corresponding state value, state action value iteration, and here we are using the max. This is again the standard Bellman's equations, and this will converge to Q star, and we shall do a little proof that it shall actually converge to Q star. So, turning our attention to the convergence proof, we shall focus on policy improvement. And for policy improvement, here's what the theorem says. The algorithm converges to the optimal policy. In other words, for all S and A, all states and all actions, the Q values will converge to the Q stars, the optimal values. And a little notation, QKSA will denote the Q value at iteration K. And delta K will be the maximum of the difference between Q star and QK. So we are in iteration K, and given any state SA, the QK SA is the value of Q at the current iteration, and Q star SA is the corresponding value at the optimum, which is the maximum, by the way, Q star. And we take this difference and we maximize over all S's and all A's. And we denote this difference as delta K. So delta K is the maximum difference between the Q stars and the Qs during iteration K. It will vary for each state and for each action. There will be differences between what the optimal values would be, which is Q star, and the current value for that state and for that action. And we therefore have to maximize over all possible states and all possible actions. And this difference, absolute value of this difference, is going to be denoted as uppercase delta K. So delta K ideally should be 0 when we have converged, because all the Qs will then be equal to their Q stars. Now this maximum over SA, since it's carried out over all possible states and actions, so it's basically the infinite norm of the matrix Q star minus QK matrix. And that's delta K. But that's just an illustration, a side point. So back to the first expression here. Delta K is easily seen to be greater than equal to Q star minus QK. Why so? Because delta K here is the maximum of all possible states and actions. It's the maximum possible Q star minus QK for all states and actions. And therefore, by definition, the maximum, if it's equal to the maximum, then it's greater than equal to the same difference for any other state SA, Q star minus QK. Now, if you notice, I had an absolute value here, but now I've opened up this, I've gotten rid of this absolute value, and that's because I assumed that the Q values were initialized to 0, in which case the QKs will keep on increasing as K increases with increasing iteration. And so Q star is always going to be the highest of all QKs. So this term in the right-hand side is always positive. So that's why we don't need this absolute value here. So this is what we have. And this implies that QKSA is greater than equal to Q star SA minus delta K. And it will be shown that delta K plus 1 is going to be less than equal to gamma times delta K. And gamma is always less than 1. So the difference, delta in iteration K plus 1, will always be less than equal to gamma times delta of K. We can think of the deltas as these differences as some kind of a error between the current iteration Q values and the Q star. So this kind of error is going to decrease in this manner. Since gamma is less than 1, this implies that delta K plus 1 is going to be less than equal to a fraction of delta K, which is going to be less than equal to a fraction of delta K minus 1 and so on, which implies that as K approaches infinity, the deltas keep shrinking and they will approach 0. Now when delta approaches 0, that means that there is no difference between the Q stars and the QKs, in which case we have converged. So this is exactly what we have to prove. And for some reasons you'll see now, let's remember this expression here. QKSA is always greater than equal to Q star SA minus delta K. So here's the proof. We begin with Bellman's equations. And here I have placed subscripts K plus 1 because this is how we update in iteration K plus 1. So this K is for iteration K. This is for iteration K plus 1. And this is the update rule within state action value iteration or Q iteration. And this is greater than or equal to R plus gamma times summation probability of the max of this. This is the only difference you see here. Here it's QK S prime A prime, and I replaced that with Q star S prime A prime minus delta K. So instead of QK, I have Q star here, and I have this negative delta K here. And why? This is a straightforward outcome of what we just observed earlier. All I've done is replace S and A here with S prime and A prime. That's why I have this greater than equal to sign, which comes right from here. Now, this max has this argument that's enclosed within curly brackets. What I'll do is I'll remove the delta K from those curly brackets here, because delta K is independent of the action that this max is being carried out over. So delta K is outside this max now. Next, I took this delta K outside the summation. Why was I allowed to do that? That's because summation of P S A S prime, the probabilities alone over all possible states should add up to 1. That's why I'm able to take this delta K right outside this whole summation. It's still inside this curly brackets with gamma being outside, and so let's open up that curly bracket. So this is what we have. This is gamma here. This gamma got moved to here. We have two gammas now once we open up the curly brackets. And so what we have is K plus 1 SA is equal to this expression here, reward plus gamma times PSAS prime times max Q star S prime A prime minus gamma delta K. And this whole expression here is Q star SA from Bellman's equation. And so we just saw that QK plus 1 SA is greater than or equal to Q star SA minus gamma delta K. This is what we just saw, which implies that I take this and move it to the left side, and I take this term here and move it to the right of this inequality, and I get the second expression here, and then I flip the left and right, and so that gives me this expression here. So Q star minus QK plus 1 is always less than or equal to gamma delta K, and which means that for every possible SA, if Q star minus QK plus 1 is going to be less than or equal to gamma delta K, then it's going to be so for the max of the difference too. So max of the absolute value of Q star minus QK plus 1 is always less than or equal to gamma times delta K. And the left hand side is the definition of delta K plus 1. So we just proved that delta K plus 1 is less than or equal to gamma delta K. Proved. Not really proof, because the formal proof is based on Banach's fixed point theorem, which is quite a bit more elaborate. The end. Before we actually conclude, let's look at some. This is today's news as I'm recording it.